Dear students, today we start a new topic, that is linear algebra. This part have a lot of theorems with a little bit calculation part, and I hope that you will enjoy the linear algebra with theorems. So today we start this topic. In this we have introduction, vector space, basis, and some other related topics in the part of linear algebra. We have seen that if determinant of A equal to 0 and the system Ax equal to 0 has more than one solutions, then it has infinite number of solutions. We will see that in this case the set of solutions has a structure called a vector space. We will first introduce the notion of a vector space. The study of matrices will be elaborated within this framework. So, we are going to define first of all a real vector space. A real vector is a non-empty set V with two algebraic operations that satisfy the following. There is an operation called addition that associate to every pair of elements x comma y belongs to capital V, a unique element x plus y belongs to V such that x plus y equal to y plus x plus bracket y plus z is equal to bracket x plus y plus z. There exists a unique element in V called 0 such that x plus 0 is equal to 0 plus x is equal to x. For every x belongs to V, there exists an element minus x belongs to V such that x plus minus x is equal to minus x plus x is equal to 0. Here 0 is called additive identity and minus x is the additive inverse of x. Another part, first of all, as we have studied about addition, and another part is there is an operation called scalar multiplication that associate to elements x belongs to V and alpha belongs to R, a unique element alpha x belongs to V such that alpha of x plus y is equal to alpha x plus alpha y. Next, alpha into beta x is equal to bracket alpha beta x. Next point, alpha plus beta with multiplication x is equal to alpha x plus beta x. And last point for this operation, like scalar multiplication, 1 into x is equal to x for all x belongs to V. The element 1 is called the multiplicative identity. The elements of vector space are called vectors. Now we have example in it. The set of reals R is a vector space. Another example, let capital V is equal to Rn is equal to x1 comma x2 and so on up to xn such that xi belongs to R where I lies from 1 to n. Then we define x1 comma x2 up to xn plus y1 comma y2 up to yn is equal to x1 plus y1 comma x2 plus y2 comma and so on up to xn plus yn, and alpha of x1 comma x2 up to xn is equal to alpha x1 comma alpha x2 comma alpha xn. Then V comma plus comma dot is a vector space. I would like to again highlight this point. The notation for vector space written as in bracket capital V comma plus comma dot. So at here we can understand by this mean that capital V vector space with plus, that is addition, comma dot, that is scalar multiplication, that these two are operations for a vector space. So it is a symbol to write vector space V plus dot. Another example we have, let capital V is equal to capital M with n comma r, the set of all n by n matrices with real entries. We define Aij plus Bij is equal to, combined in bracket, Aij plus Bij, and alpha ij is equal to, in bracket, alpha ij. Then V is a vector space. Another example is, let capital A be a m by n matrix, then capital V is equal to x such that Ax equal to 0, then the set of solutions of Ax equal to 0 is a vector space. It's a very important example, kindly note this one. Next example, let V be the set of all polynomials with real coefficients and degree less or equal to n minus 1 for P of x is equal to summation I equal to 0 to n minus 1 ai x raised to I, and Q of x is equal to summation I equal to 0 to n minus 1 bi x raised to I, comma, alpha belongs to R. We define following: P plus Q of x is equal to summation I equal to 0 to n minus 1 ai plus bi with x raised to I, and second one, alpha into P of x is equal to summation I equal to 0 to n minus 1 alpha ai x raised to I. Then V is a vector space with additive identity or the zero polynomials. We have to notice the remark: the sum of two nth degree polynomials may not be a nth degree polynomial, hence the set of all nth degree polynomial is not a vector space. We remark because in above example we have to say that V is a vector space with additive identity or the zero polynomials. Now, after definition of real vector space, we have to understand complex vector space. Definition is as follows: a complex vector space is where we can choose alpha belongs to C and the scalar multiplication satisfies the following: alpha of x plus y is equal to alpha x plus alpha y. Next point, alpha into beta x is equal to alpha beta into x. Next one, alpha plus beta into x is equal to alpha x plus beta x. And last one, 1 into x is equal to x for all x belongs to V. For example, Cn, capital M, n, C, etc. are the complex vector spaces. Now, after definition of vector space, we are going to define vector subspace. Let W be a non-empty subset of vector space V, then W is called a vector subspace of V if W is a vector space under the operations defined in V. In order to show a vector subspace, there is no need to verify all the rules defined with vector space. it is enough to check that 0 belongs to W, W1 plus W2 belongs to W for every W1 comma W2 belongs to W. Next one, alpha W belongs to W for alpha belongs to R and W belongs to capital W. The other rules are satisfied accordingly. Now we have an example on subspace. The set capital A is equal to x comma y comma z such that x plus y plus z is equal to 0 is a subspace of R3, but capital B is equal to x comma y comma z such that x plus y plus z equal to 1 is not a subspace of R3 as 0 does not belongs to B. Another example, the set of all polynomials of degree less than equal to n minus 2 is a subspace of all polynomials of degree less than equal to n minus 1. Next example, the set of points on a straight line which is not passing through origin is not a subspace of R2. Next example, the set of points on a circle is not a subspace of R2. Next one, as a part of example of vector subspace, we have the union of two straight lines passing through origin is not a subspace unless both are same. Last example on it we have on vector subspace as the set 0 is always a subspace of any vector space. So these are the part of introduction as well as definition and examples on vector space and vector subspace with real and complex plane. So in next topic we continue with some others part of this linear algebra, and I hope that you will all memorize and try to understand the definitions with example, and then we have further some another part of the topic and some other examples. Thank you.